Okay, here we are on part 3, problem 61, and I already started to draw this little orbit. It says, so if a satellite is spinning clockwise, what direction is the force? Well, let's look at this real quick. So we've got the satellite here, we've got the orbit circular, and then the Earth's in the middle. Well, what is the force keeping it in orbit? That force is gravity. Otherwise, if you launch out a satellite, it'll just keep going straight forever. But if you have the gravity of the Earth, it makes it go in a circular orbit. And this is just like the pendulum, where the string tension is always pointing to the center, where the string is attached, where the hinge is or whatever. Same with this. Gravity is always pulling in. And so we could put the gravity force to the inside, and no matter where you're at, if we have a satellite here, it points on the inside, satellite here, points on the inside. And this is what keeps it from keeping going in a circle. It has to keep pulling in. So if the satellite's spinning clockwise, what direction is the force? Well, depending on where the satellite is, but it's always pointing to the center of the Earth. What direction is the acceleration? The acceleration is the same direction. Now, and that kind of goes along with what we were talking about before, F equals ma. If the acceleration, so the force goes in the same direction as the acceleration. And that's kind of what Newton's law is talking about. When it says F equals ma, it creates an acceleration. So, answer to 62, it's the same as 61 toward the center of the Earth. Now, don't get confused at the velocities, because the velocity is going this way. It just keeps going the direction of the circle, right? Because that's the way it's moving. But velocity and acceleration aren't always in the same direction. In this case, they're right angles from each other. So with that in mind, if the force that keeps the circular motion goes away, what direction would the satellite go? So if we lost this force pointing to the center of the Earth, where would it go? Well, let's bring this back to if we have... So this problem is just like if you had a ball and a ball on the end of a string. And so think about this. If you have a ball on the end of the string going to the center of the Earth, and the string breaks, I used to think, you kind of want to think, since the string's pulling it in, the tension from the string's pulling it in, then when we break the string, that it will go out. Just if you're swinging a string around your head with a ball on the end. But that's not true. It's not true that it'll go out. It'll actually go this way. Because, think about it, the velocity is going this way, and the velocity at every point is going this direction. And it's the direction tangent to, we call this tangent to the circle. So same with the satellite. All of a sudden, the satellite's going around in orbit, and then all of a sudden gravity disappears, the Earth blows up, or I don't know, somehow there's no gravity, and so then the satellite just heads out this direction forever. And just like that first law of Newton's first law, it'll keep going the same direction forever, unless it's acted on by some other force, gravity, or whatever. So at any point the string breaks or gravity disappears, it'll keep going the direction of the velocity. Alright. And yeah, we say tangent to the circle for that. Okay, 64. It's a little different. Alright. Okay, here's a work problem. So, you do 600 joules of work. So work equals 600 joules. To move a box 20 meters, so distance equals 20 meters. How much force is required? Force, we don't know. Okay, this is an equation worth memorizing. It's pretty simple. Work equals force times distance. So we know the work, we know the distance. What's force? Well, let's solve this equation for force. So we divide both sides by d. So we get force equals work divided by distance. And then just plug this stuff in. Work is 600 joules. Distance is 20 meters. Okay. Before I divide this, I just want to change joules into something else. Because if we're going to divide joules divided by meters, another way to write joules is Newton meters, Newton times a meter. And you'll see how those meters are going to cross off in a second here. So 600 divided by 20, that's 30, and then meters cross off, 30 newtons. And just a reminder, Newton times meter is a joule, same thing. Alright, that was 64. Okay, in the previous problem, okay, 65, if you can do the previous problem in 5 seconds, so time is 5 seconds, how much power is used? Well, here's another equation worth memorizing. Power equals work divided by time. So our work was 600 joules. Our time was 5 seconds. 600 divided by 5 is 120. And then we have joules divided by seconds. Okay, joules per second, that happens to be the same thing as watts. It's the definition of watt, is a joule per second. 120 watts. That happens to be what our light bulbs are. Kind of weird. But they're really the same thing, except this is electrical energy. This is mechanical energy, like energy of moving things, where your light bulb is electrical energy, and they could be converted into each other. If you have an electric motor, it turns electrical energy into mechanical energy, but they're the same thing. Okay, now let's go on to 66. Okay, this is just summing forces. Here we go. So I'll just say all these forces are acting on the center of mass, right here. One force is applied to the right at 4 newtons. 4 newtons. And another is applied down at 3 newtons. 3 newtons. What is the magnitude of the net force? Well, when we find net force, what we want to do is add these two vectors together, these two forces. So let's start. So the way we do this is we start at the center of mass right here, and then we go from we take this vector, it's 4 newtons, and then let's move this vector over to the end of this vector. That's what we do when we add vectors. So we move it over right here. There's our 3 newtons. Then our net force is going from here to the end here. So that's this right there. If you haven't noticed, we have a cool little right triangle here. So let me redraw that. We have 4, 3, and the hypotenuse. Okay, since this is a right triangle, we can use the Pythagorean theorem. So that this could be A, this can be B, and we don't know what C is. But we want to find C. That would be that's our resultant force or our net force. So A squared plus B squared equals C squared. We know A squared, 4 squared plus 3 squared equals, we don't know what C is. Okay, we want to get C by itself, so square root both sides. And so we have square root of 4 squared, that's 16. 3 squared is 9. Equals, and then these cross each other off, so C. This is our resultant force. 16 plus 9 is 25. It just so happens that 5 equals C. So C, that resultant force is 5 newtons. Right here, that's 5 newtons. 5 newtons. That's how you do it. What's the net force? 5 newtons. Okay. This is as far as we're going to go on this for now. Let me know how this goes. Let me know if this was helpful. Obviously, online tutoring is nice because you could actually ask questions. Let's see how this works, and if it's effective, maybe we'll do it more in the future. All right. Good luck with everything, Marvin. Okay, see you. Bye.